I'm going to go through my electricity slides. Those of you who I've taught will recognize some of the slides. So um, as you know, those of you in year 11 are probably now studying electromagnetism, or you will be. And when you finish that, I'll probably be giving you a test on electricity and electromagnetism because the two are connected. So here's a nice starting slide showing that there's a brown wire, which is the live wire, and a blue wire, which is the neutral wire. And obviously the difference in voltage between the two is, if it's a mains electricity, it would be 240. Well, it is possible to spark across air as long as the voltage per centimeter is over a certain value. And that's, you may have seen sparks when we used the Van de Graaff generator, which produces quite a few thousand volts. And if you put a neutral object like the blue wire close to it, the electricity can jump across it. So I just basically took this picture from the internet. Hopefully YouTube won't mind it when I upload it. That sometimes they look for copyrighted images, but I just thought it was a nice picture to share with you. So there you got mains electricity, brown wire live, blue wire neutral, and electricity sparking across a gap in air. So that's what lightning is. Lightning manages to jump across from the clouds right down to the earth, which is considered the equivalent of being neutral, and the clouds will be charged. So if there's enough potential difference between them, then it can break down the air in between them, and that's what a spark is. Okay, so static electricity, you can also create it when you rub two materials together. So for example, if you rub, I don't know, say a polythene rod, it won't lose its electrons, it will gain electrons, more like the diagram on the right. The electrons will jump to the polythene from the cloth, but there may be other materials, like the diagram on the left, where they lose electrons to the material. And this is all to do with the chemical composition of different insulators, and because they're insulators, once you charge them, if you don't touch anything with them, they will keep the static charge buildup on them. And if you remember, I managed to show you that a charged rod can actually deflect water coming out of a tap if the tap flow rate is slow, and it always amazes students the first time they see that. And that's because water also has charges in it, hydrogen and oxygen. The oxygen is more negative than the hydrogen is more positive. And if you study chemistry later on, you'll understand why. Okay, so although atoms or molecules can be neutral in total, they do have positive and negatives in them, as you know. Okay, so static electricity is a buildup of charge, and it's static because it's not really moving once you've moved it across from one material to the other by the transfer of electrons. Remember, that's what you've got to say in the exam. And static electricity will only come up in the paper 2 if you're doing GCSE Edexcel physics. It won't come up in paper 1, which is the one that combined science use. Okay, so if you're doing combined science, you just need to appreciate that static electricity is conceptually a very important part of electricity, so you should still listen to it, but you won't get as many application questions about it. So just like magnets attract and repel, if you got positive and negative, they will attract. If you got negative and negative, they will repel. Okay? So when you're doing magnets, there'll be north and north repel, south and south repel, north and south attract. If you manage to charge a Van de Graaff generator, or you've seen it, you'll notice that the dome actually becomes positive. The metal, the dome is made of metal, it's insulated, yeah? And the rubber basically takes the electrons and away from the positive dome. Remember, metals are in group 1 or 2 often in the periodic table, and they have 1 or 2 free electrons, so they're easy to lose those electrons. So when you talk about chemical bonding, that's why they become the positive ions, because they give away their electrons to, for example, group 7. So you can have sodium giving electrons to chlorine and creating ionic bonding. So this is the same principle, that the metal will lose electrons easily, the rubber will gain electrons. So it's a bit like the cloths, what we did here when we're charging rods here you'll see that the charge will go from one material to the other. It's the same in the Van de Graaff generator, that the metal becomes the positively charged object. So if you touch it, you'll also, if you're insulated, you will also lose your electrons through the dome to the rubber belt, and that's why your hair stands up, because it repels itself. Okay, now if you attach the dome to a wire, like I have here, going to Earth, and this is a symbol for earthing something, well, it can then regain the electrons from Earth, because Earth has excess of electrons, and they will be attracted up to the positive dome, and that will neutralize the Van de Graaff generator. Okay, you use static electricity in photocopiers. For example, the ink in inkjet printers is attracted to the paper because the paper becomes statically positive or negative, and the ink is then attracted to it. Okay, so the positive place, then step 3 and 4, the ink then sticks to the positive P shape that is formed due to the photocopier that's producing the printout. Okay, so this is only for those of you in doing triple science. It will allow you to make your notes, so I'll let you stop that and struggle through the answers on your own, and you will be able to find answers like this if you get those revision books, CGP. I'm not going to go through every answer, okay, with you. I'm just showing you what kind of things that you need to know for your revision if you're doing triple science. That means you're doing physics as a standalone GCSE. Okay, they're also used in chimneys, sometimes to stop the smoke from escaping. So if the smoke goes through the positively charged grid at the bottom, it will become positively charged, and it will be attracted to the sides of the chimney stack if they've put negatively charged plates on each side. So it stops the smoke from going into the atmosphere. Okay, so you get cleaner air by using smoke precipitators. So it's another use of static electricity. It's an application of it. So it'll make you think. It's basically an application of electricity. Okay, you also, so as well as photocopiers, you can also use them for spraying paint on cars. Yeah, so if you make the body of a car a certain charge and the paint the opposite charge, you'll get a smoother finish to the paint that you're spraying on the vehicle. So they use this for spraying paint. The dangers are fuel pipes. So you should always switch off your engine, because if you can get a spark, it can cause an explosion, just like a spark that I showed you in the opening slide in the PowerPoint. And in hospitals, you need to look at the applications. In static electricity, for example, if they want to resuscitate someone, it's a build-up of static electricity in the plates. They build up this static electricity, and they give you a shock with the two things that they put on your chest when they want to. They call defibrillators, yeah? So these are the applications of static electricity that you need to look up. But the best thing to do when you're revising is get one of those CGP revision books, and they give you a more complete set of notes than I'll be able to cover in this PowerPoint. Okay, then coming to DC circuits, we would use batteries and cells and different types of resistors, ammeters, voltmeters, filament lamps, switches, LDRs, fuses, diodes, thermistors, and fixed resistors, and you need to know all these symbols. So the variable resistor is the one with the arrow, the diode is the one that looks like a funnel, and the electricity only flows in one direction through them. The switch is there. Bulb or filament lamp is the one with an X. Voltmeter and ammeter, you need to know how to join them in circuits. LDR, the arrows represent the light, and the resistance depends on how much light it is shining on it. And the light effectively is frees more electrons. So in a device like a light-dependent resistor, it's actually made of a non-metal. It's a semiconductor device, and the more light shines on it, the more free electrons it gets. A fixed resistor, is just a rectangle like that. A cell is a single unit of a battery, yeah, which is the top left. A fuse is a very thin piece of wire which has a symbol like the resistor, but a wire going through it, and it melts at a certain current. If the current gets too high, it's a safety device. Thermistor is a heat-dependent resistor, and the ones you use in GCSE, the higher the temperature, the lower the resistance. Like an LDR, they are negative correlation with, in this case, temperature. The LDR is negative correlation with light. So if you increase the temperature, you free more electrons, and the resistance decreases for these types of thermistors. So you need to know how these all work. So battery is a multiple unit of cells, okay? So when you go to the shop and buy a battery, you're actually buying a number of cells, and they're just called batteries in everyday life, okay? A car battery, for example, is made of 6 cells using lead and acid, sulfuric acid, and the 6 cells together are 2 volts each, and they give the 12 volts for your starter engine to start your engine in your car, okay? Electrical energy is a measure of how much voltage you supply to the circuit, and it basically converts chemical energy in the cell, yeah, into electrical energy in the bulb, okay? So if you've got one cell, you need to only use a 1.5 volt filament lamp or bulb, okay? So again, if you've been in my classes, you'll have had notes on this already, and this is really just for you to revise before your next unit tests, which will be after you finish electromagnets. So electrical energy is basically how much energy the electrons gain by being connected to a battery. And really what's happening is the electrons which are negative are being attracted to the positive side of the battery or the cell, and the battery or cell is a chemical device which is made of different materials, and one side becomes the positive and the other side becomes the negative, and you don't need to know for physics how they work internally, okay? So the energy is not what's going around the circuit, it's the electrons or the charges which go around the circuit, but the charges, like the electrons, gain the energy from the battery and deliver the electrical energy. It's transferred from the battery, electrical work is done, and the bulb then changes it into light radiation, which then is transferred to the room, okay? So it's an electrical transfer of energy. Electrical current, on the other hand, is a flow of usually electrons, negatively charged particles in a circuit, but when the electrons go from negative to positive, that's what's happening in a metal, and the wires connecting the battery or the cell to the bulb are made usually of copper wire, insulated. So the electrons gain the energy to be attracted to the positive end, and when you put a wire from the negative end of the cell to the positive end of the cell, yeah, the electrons will gradually drift through there and they give up their energy to the bulb and make their way to the other end of the chemical device called a cell, okay? But when you want to define what an electric current is in words, you've got to say it's the rate of flow of charge, because obviously if you have more batteries, you're having a bigger voltage attracting the electrons, so they actually can increase the current through the wires. So you've got to always make sure you say current is the rate of flow of charge, not just the flow of charge, okay? So the box in the red is what you've got to remember. But internally it's electrons flowing, but it doesn't have to be electrons, okay? In other situations it could be positive charges flowing. For example, when you're electroplating using electrolysis in chemistry, sometimes there are positive ions which are transferring charge as well. Electrical power is measured in watts, and it's the rate of transferring energy. So just like current is the rate of transferring charge, power is the rate of transferring energy, yeah, joules per second, and it's given, you can also calculate it by multiplying the voltage by the current, yeah, and that gives you the rate of transfer of electrical power, okay? and these are questions for you to try in your own time. I'm not going to go through them. The triangle will allow you to work out which one's which. Just remember the current is in yellow, so the symbol used for current is a capital I. Okay? I always tell my students it's indicated current. The reason we don't use C is because C is the unit used for charge, which is measured in coulombs. Okay, so conventional current, although we know electrons are usually the things which are flowing in wires, and we know they go from negative to positive. However, electricity was discovered before the electron, and the convention then used was that the current flows from positive to negative. So that's the definition of what conventional current is. And when you're drawing a circuit diagram, you always have to draw the current in a circuit diagram as going from positive to negative, even though internally inside metal wires it's 99% of the time electrons which are transferring the charge. Okay, so you need to know the definition of conventional current. Basic ideas so far covered. Electric current is when electrons start to flow around a circuit, and we use an ammeter to measure it, and it is measured in amps or amperes, whereas potential difference, also called voltage in more general terms, is how big the push on the electrons is. Yeah, I don't really like that term, but it's often used in physics books. I prefer to say potential difference is how much energy the electrons received in the circuit from the battery or the cell. Okay, because the units of voltage is actually equal to joules per coulomb. Okay, it's not a push, which would be newtons. Okay, and we use a voltmeter to measure it, and it is measured in volts, a unit named after the Italian physicist Mr. Volta. Okay, and then resistance is anything that resists an electric current or impedes it. Okay, and that resistance is measured in volts. Okay, so resistance is measured in volts. So more basic ideas: if you've got one bulb attached to one cell, then it will give the normal brightness if it's a 1.5 volt cell. If you then connect two cells to it, it will glow more brightly. If it's too much voltage for the cell, however, it will break the bulb. The filament will overheat. Okay, so as long as you're staying within the maximum capacity of the bulb, it should get brighter if you put two cells. So if a battery is added, the current will increase because there is a greater push on the electrons. That's what they want you to know, or I don't really like that, as I told you before in the slide before. There's a greater current. Okay, there's more energy given to the electrons, would be more accurate. Okay, there you go back to the initial circuit, one cell, one battery. If you now put two cells in series, one cell and two bulbs in series, now they will glow more dimly because they have to share the voltage of the battery, whereas in the circuit above on the right hand side, all the voltage is kept by one cell, so it gets double voltage, double amount of energy per unit coulomb per charge, and here they're sharing only one cell's worth, so they'll glow very dimly. If a bulb is added, the current will decrease because there is a greater resistance in the circuit. Okay? So in the top one, I would change the wording to, if a battery is added, the current will increase because there is a greater potential difference across the bulb. That's the better way of saying it. Okay? Now, current in a series circuit is the same wherever you put it. I apologize, my cat, who is meowing rather loudly, she wants food. If the current in here is 2 amps, then the current will be 2 amps wherever you measure it in a circuit, and you could do this with a series of ammeters to prove it to yourself. So current in a series circuit is the same at any point. Okay? And current in a parallel circuit, however, it has a choice of routes, and if the current is going this way, it's going the wrong way. Look, it's not conventional current they've drawn here. The current is going one way, it will split between the two bulbs and then join up when it comes to the other side. And if they're identical bulbs, they will get exactly half the current each. Okay? and they'll join up. You never lose current. So in a parallel circuit, the current is not the same everywhere. It depends on how many pathways there are for it to split up and then rejoin. Okay, but the total current coming out of the cell will be equal to the total current going, the sum of the currents going into each path. Okay, and then here, say if you've got 6 amps there, then you get, if they're identical bulbs, you get 2 amps there, 2 amps there, 2 amps there, and then 6 amps when they all join up again. And in between, you can work out how much it will be. Okay? I'll have to stop soon because my cat wants feeding. Okay, so here's some example questions that you've got to work out. If there's 3 amps and the bulbs are identical, how much will each bulb get? Yeah? And if there's 6 amps, the second question is a bit more difficult. There's 1 bulb in the first part and 2 bulbs in the second path. Well, this one has a bigger resistance. So over here, if you've thought about it, they'll get exactly 1 amp each. Yeah, so 3 amp comes out here, 1 amp goes there, 2 amps goes down, 1 amp goes along here, 1 amp goes there. It's exactly the same. Well, when you got 2 bulbs in this path and 1 bulb in this path, remember this one will glow more brightly because it's got the whole of the 2 batteries in contact with it, in connection with it. Yeah? So in parallel circuits, these 2 bulbs will share the battery voltage, whereas this one will get all of it. So this one will actually glow more brightly, and that's because it actually gets a bigger share of the current. This one will get 4 amps, and this one will get 2 amps. And that's the kind of problem that confuses students at GCSE, and you need to make sure you've done a lot of past exam questions on these to work them out. Okay? If your school does physics clinics, I recommend you going to them to ask questions that you have. Okay? Because not everything can be covered in a video. Okay? So here now we're going to do voltage in series circuits. So if you've got a battery supplying 3 bulbs, basically the supply voltage, that means the battery, what the battery provides in voltage, is going to be shared between 3 bulbs. So what you provide here gets used up by these. These are consumers of voltage, and this is a provider of voltage. Okay? So if we have 6 volts there, and a voltmeter is checking that we do, then if you put a voltmeters and the bulbs are identical, yeah, then they will share it in exact amounts. So you're going to get 2 volts across each bulb. Okay? And if you put a voltmeter across 2 of the bulbs, then the 2 bulbs will get 2 volts each, so it'll be 4 volts in total. Okay? So in a series circuit, the voltage is shared between the components. And remember, voltmeters always go in parallel, whereas when we had the ammeters, they go in series. So voltage in parallel is actually quite easy. If you have a 4-volt battery, each bulb will get a 4 volt of energy per unit coulomb. So the bulbs will be exactly 4 volts each. Okay? So they'll get exactly 4 volts each because they have a direct access to the battery. But the battery will drain itself more quickly the more bulbs you have put in the circuit in parallel. Each one is using up power. Okay? Voltage times current. And a summary of series and parallel circuits. In a series circuit, the current's the same at any point. In a series circuit, however, the voltage splits up and is shared between each component. Okay? But the total voltage will be the same as whatever the supply voltage is. In a parallel circuit, the current splits down each strand and then joins up again, but the voltage is the same across each strand. So that's really a good place to stop and allow you to consolidate your understanding. There are some slides that are coming ahead, but if you found this useful and you want more videos like this, you have to give me a like, share the video with your friends, and if I get lots of likes and shares and I get more subscriptions through these videos, YouTube tells me how much each video adds to my likes, my share, and my subscriptions, then I'll make more videos. But if I don't get any likes and shares, then I'll make other videos, because my main focus on this channel up to now has been students preparing for A-level exams, okay? And I'm just starting to add some GCSE revision PowerPoints for you. So please do that, if you found it useful. Here's a really complicated one for you to try, so you can stop the video and see if you can work out all the missing currents A1, A2, A3, and all the missing voltages V1, V2, V3. It's an application of what I just taught you, yeah, which is this. So it's like a puzzle, you've got to work it out. So I'm going to let you struggle. For those of you in my classes, I usually go through this as a quick check after we finish this part of the topic. And here's a more complicated one. And here you've got 3 bulbs in the top path, 2 bulbs in the bottom path. So the voltage, the current will be split 3:2 ratio. Whereas in this one, the current will be split in a 1:2 ratio, and you've got to work out which way. So these are 2 different problems for you to try. Okay? I'm not going to do Kirchhoff's first law now, but Kirchhoff's first law is basically the first rule, the first rule in the parallel circuit to do with how current splits up in each strand. Okay, I'm going to stop the video there, go and feed my cat, and hopefully get lots of likes and subscriptions from this. It is appreciated if you do that. Thanks for watching, and hopefully see you in the next video. Bye for now.